Hello, everyone. It's my pleasure to introduce our speaker today, Yanni Yuval. And Yanni is a research scientist at Google Research, working on the development of hybrid climate weather models. If you look at this very cool animation, it's from the near GCM. And he completed his postdoctoral research at MIT, where he worked with Paul Gorman on hybrid atmospheric models that also incorporate machine learning and climate physics. For example, machine learning for convection parameterizations. His academic background includes a PhD in atmospheric dynamics and a Master of Science in soft matter physics from the Weizmann Institute of Science. And with this, let's welcome Yanni.
Then I'm going to talk about neural general circulation model for weather and climate. And sometimes I have a tendency while I talk to accelerate my pace. So please mark that I'm unclear or something, feel free. So I'll start with an introduction, trying to highlight that we still have uncertainties in climate projections, errors in climate models, in weather models. And I'll try to make the case why we are in a pretty special point in time that we can take these physics-based models and couple them to machine learning components using the data that we have for training them. And I'll try to make the case why we haven't kind of successfully created a hybrid model that really outperforms existing model. And then I'll spend the rest of my talk talking about the differentiable atmospheric model we have been developing. And I think that it kind of gave a big step forward towards outperforming existing models. I'll talk about how we use it for weather forecasting, for ensemble forecasting, and what ability it gives us. Then I'll talk about what I'm more interested even in what it gives us in terms of being able to simulate the climate on Earth currently. And the last part of my talk would be something that was not included in the recent paper we published, was how we use nowadays observations to learn stuff and how it really substantially improves the ability to simulate certain aspects of the atmosphere. So let's start with the introduction. So in terms of motivation, we have many aspects in the climate system that we don't simulate very well. One of them is extreme precipitation. It has huge societal impacts, and I think that there is a big effort to improve this ability. And I would argue that we haven't been super successful in it. And so we want to answer questions like what happened, what is our current climate, what is 1 in 1,000-year storm looks like, how extreme precipitation changes when climate warms. And people have tried to use all sorts of tools to do that. One of them is here I'm showing a plot using observations, so literally gauge measurements, to try to estimate how extreme precipitation changes when climate warms. And here we in this paper, many stations were aggregated together to try to ask a question. In the y-axis is the sensitivity the sensitivity of extreme precipitation to increase temperature. The x-axis is the latitude. And what you can see that on average, when you aggregate a lot of data across latitudes, you see basically a signal of increasing precipitation. This is the bold line. But you can see also that there is huge uncertainty, especially in the tropics. You can see that any number between 25% almost increase in extreme precipitation per degree of warming to 0 almost. So there is huge uncertainty. And it's not only that we have huge uncertainty in this plot, when we're even trying to focus more and asking the questions that we really want to know, like going locally and asking, so how extreme precipitation changes locally at a place that you are interested in, we just don't know, at least not from observations. So because we just don't have enough observations to determine trends in extreme precipitation locally. So what people do, they use semi-class models, they integrate them forward, different climates, and try to plot something like that. Here, colors indicating how extreme precipitation changes when climate warms. Blue regions are regions where extreme precipitation increase. And you can see that basically it's really non-uniform. There are regions, let's say like the Mediterranean here, that just there is no clear trend of increased precipitation. However, we are really uncertain in these numbers. Because models have very large differences. So here I'm plotting the standard deviation. So basically, different models give just different results for the sensitivity. And where you have, you can see that in certain regions, we are talking about 20% increase uncertainty or standard deviation across models per degree of warming. So literally, we are just uncertain, and we can, I'll just close that. And it's not only that there is big variability, I would argue that models just don't do well in simulating extreme precipitation. I'll get into it a bit later more. And it's not only extreme precipitation, there are multiple things you can look at. Here, I'm looking at biases in precipitation. So literally, how well can we simulate the climatology of precipitation? On the left, you can see 3 different models, colors indicating biases across 20 years in Northern Hemispheric summer. And to get us to decide whether this is a big bias or small bias, on the right, it is plotted the trends from literally from climate projections going 100 years forward or 80 years forward. So the biases we currently have in models are just larger than the trends we see. So I could have chosen different examples. We have uncertainty in temperature projections, in circulation projections, but the point is that we have large uncertainties. And I would argue that the main source of uncertainty is still the inability to resolve certain processes in our parameterization. So just to make the case, this is a caricature of a climate model. What we want to plug inside is the laws of physics from fluid dynamics, thermodynamics, etc. But we solve these equations on a grid, on a discrete grid, somewhere between 50 to 100 kilometers. And the problem is that this discrete grid of 50 by 50 kilometers encapsulate like multiple physical processes. We have clouds there, we have convection and turbulence, interaction between radiation and clouds. And all these zoo of processes are not resolved in current models. And this has been known. And we cannot ignore it. It has tremendous effects on our climate system. And what people do, they develop parameterizations. So basically, these parameterizations are simplified theories, semi-empirical models that we tune that target specific processes. And the reality is that although people have been working on parameterizations for decades now, and they have been improving them, but they are still the main source of like model errors in general. And this is unsatisfactory situation. And this is where hybrid models came in. I would argue, like, I don't know, maybe a few years ago, the first papers started to emerge. And the idea is that we can use a different approach for a parameterization. Instead of being like using simplified theories or all sorts of semi-empirical approximations, we'll just use a data-driven approach. And the main theme looks like that. We will take somehow high-quality data, can be observations allegedly, it can be reanalysis data, it can be high-resolution models. Somehow we will learn something from them, and this somehow is very difficult. I'll make a case. We'll plug them into our atmospheric model or climate model. We will accompany it by the laws of physics that we all like, and we will have these amazing hybrid models. They will outperform existing models. But the reality has been quite different, I would argue. And there has been like some success in creating these hybrid models, but there has been, I would argue, a lot of persistent limitations when you're coupling these two systems together. And just to name a couple of them, many times you get unstable simulations, so literally blowups, numerical blowups. Sometimes you get climate drift. You try to simulate certain climate and it's getting warmer or drier. And even if in the cases this didn't happen, the reality is that in realistic scenarios, we don't have really improvements compared to traditional models. There is no hybrid models that are really outperforming in zoom out, not like specific metric like existing models. And the question is why? And I will try to answer this question today, and we'll make the case why we need differentiable modeling and try to show our results. So there are many limitations of hybrid modeling currently. So you can, to answer this question, why people, including myself, try to argue maybe they don't obey physical constraints. And I've made some work on it, some other people have made work on it. But today's topic is that I would argue that we're just optimizing completely the wrong metric when we're developing these hybrid models. And this is why we need differentiable atmospheric model. And if you are like, I will try to explain soon what does it mean. Okay, take a deep breath and let's go into the results. So what is a differentiable atmospheric model? Now I want to kind of like give the gist of how hybrid models were developed so far. The idea was that we have some kind of a data set that we trust, and we have it at different time instances. And the idea is that we still want to keep our physics-based code. It can be a dipole for the atmosphere, for atmospheric simulations. And we want to somehow, the network, to help us basically follow the path of the data that we trust. And the idea was that we somehow while having this data from models, from reanalysis, diagnose the missing term that we need to add at every time step. And we will develop these kind of data sets that for a given atmospheric state or oceanic state, what we need to be the tendency that the neural network or subgrid parameterization needs to spit out. And this is the hope was that this is how we will fix our models. And this has a big problem. And the problem is the following. Besides being that it is a very difficult task that I won't get into, like how to diagnose those missing terms, and people have used various methods, and the real problem is that when we are really using the models, we are using it in a completely different scenario. We are not optimizing it over a single time step, that this is what we have tried to do when we developed so far all these hybrid models. We just told it, we have a time t, we want it to get to that the network will help the model to get correctly the state at x time t plus delta t. The problem is that when we are really using these models, we are running them for many, many, many time steps. And the neural network, when it learned, it has never interacted with your physics-based code. It just is completely unaware of it. And when you couple them together, you can imagine many things go wrong. One of them, that it will give rise to unstable modes, for example, and you get instabilities. The other is, for example, let's say you have a super accurate neural network, but it just adds a bit of energy or takes a bit of moisture out of your atmosphere. When you run your model for 10,000 time steps, you will start seeing that issues. And this is maybe why you get drift. So this is really unsatisfactory situation that you basically are tuning your neural network to do one thing, but you are testing it in a completely different scenario. The testing meaning like really running the model. And now I want to take a detour and talk a bit about pure machine learning models and what we can learn from them before I go back to hybrid models. So the advantage, one of the advantages of pure machine learning models, that they don't need to do this like offline learning. What do I mean by that? Let's take, if you would have a pure machine learning model, a neural network that allegedly step forward your atmosphere, you can run it for multiple time steps, stop the model, and then optimize back. Why you could do that? Because neural networks are differentiable. You can basically optimize a loss function and change the parameters accordingly over multiple time steps. And this is a really desirable thing, because now if you want to, let's say, predict 5-day weather forecast, but your model just propagate your model 1 hour, you can just run it 120 time steps, stop the model, and back propagate through the weights and optimize your weights of your model that propagates the atmosphere. Please raise your hand if it was like, I felt I was swallowing words. But eventually what it gave pure machine learning models to do, they could now take data, typically what they use, they take reanalysis data from ERA5, use initial conditions from ERA5 and try to optimize it over multiple time steps. And these kind of models have created, I would argue, a revolution in weather forecasting. So here I'm showing the skill relative to ECMWF IFS. So the best physics-based model is in orange. These are the years, and each dot is a different paper and the year it emerged. And you can see that a year and something ago, we had already the first 2 models that outperformed the best physics-based model. However, these pure AI models have issues. And here I'm showing one of the most popular pure AI model, GraphCast on the right. On the left is ERA5 reanalysis for 10-day weather forecast. And what you can see that these pure ML models typically blur out. So they are not really physically realistic, although they are really skillful in their root mean square error metric, or whatever metric you want. They just don't resemble the atmosphere in many senses. You can really distinguish between GraphCast and ERA5 after 10 days. And this has really big consequences. You cannot run really ensemble with them or probabilistic forecasting. And it's really a problem if you're interested in climate, because your model becomes blurrier and blurrier and doesn't represent really the atmosphere. Okay. And the last question before I go to what we have done is we needed to understand why machine learning models are blurring. And I will argue because they are using the wrong loss function, essentially. So most machine learning models are using just mean square error. They're trying to optimize it. And let's think about the problem of that. Let's say you have an observation in black. You can think about it as a tropical cyclone located somewhere. And now your model has 2 options. it can predict a tropical cyclone in the wrong location because it's difficult to predict accurately where it is, or it can predict no tropical cyclone. In terms of mean square error, the second option is better. But in terms of usability, the first option is much more preferable, because if you are going to have a tropical cyclone, you want to predict it, even if it's slightly in the wrong location. So basically, what happens at mean square error rewards you for averaging over uncertainty. When you have uncertainty, like the case of weather forecasting, mean square error just encourages you to blur out because you're averaging over your uncertainty. I should say that there are different approaches nowadays. Really recommend to read this paper of Gencast. So let's make a stop and tell our goal for the next like 20 minutes. Our goal is to build a hybrid model that is both competitive with pure machine learning models. And for that, we will have to optimize it over multiple time steps. So it will be differentiable. This is the differentiability property that we can differentiate through it. And we want to correct things that machine learning models do wrong. So to get really sharp forecasts, we want to get a probabilistic forecasting to really have an ensemble of weather forecasting. And we want to be able to run climate simulations and compare to existing models and hopefully outperform them. So yeah, I think I've said all this, sorry. Great. So let's talk about differentiable modeling. So the problem so far was that most of physics-based code was written in languages or in a way that is just not differentiable, like in Fortran or other languages, even Python. But Python has, you can write in Python in a differentiable manner. And again, what does it mean that we have developed a differentiable dynamical core? It's just the same physics-based model, just written in a way that you can differentiate through it. So you can ask the question, how should I change a parameter or a set of parameters in my model in order to optimize certain loss function? So this is how you optimize anything. Like you can think about weights in neural network, you can think about some other parameters in the model, but this is just what it means. It's a code that is written in JAX that allows us to run our atmospheric model for multiple time steps, stop, and then ask the question, how should we change the parameters in the model in order to get a better weather forecast, for example? And to do that, and the second step, so this was kind of the first point. It was very painful process and long process to do that. And now once we did it, we got to the point that we need to start optimizing our model. And we want to encourage it not to create blurry states because we want to realistic like atmospheric states. And we have used two different methods. We have used two different sets of loss functions. So I'll try to describe both because I think it's interesting if you're coming from the machine learning world. So one is deterministic and one is stochastic. Let's talk about the deterministic loss function that we have used. So the problem was when we are using mean square errors that basically we are requesting the model to predict something that is not really predictable. We are telling it, please minimize the error of something that we know that it has basically chaotic behavior. You cannot predict it with certainty. So the idea that we have looked at was to say the following. What you see here on the y-axis is the error of a physics-based model versus the length versus the time it predicted. Colors are indicating different wave numbers. So what you can see is that large wave numbers, like wave number 100, you have very little predictability. Very fast, you're losing the predictability. You cannot predict small-scale features for very long. It's just like the error growth there is faster. However, the large scale or low wave numbers are much more predictable over time. So the idea was that instead of asking it to predict accurately everywhere was to say, okay, instead of being your target being, let's say, era 5, your target will change with time in a way that we are washing out the small scale details. Now we don't ask you to get the small scale details, let's say after 48 hours, because we know it's just not predictable, but we're still demanding you to get the large scale errors. So we are progressively filtering our target. This is kind of counterintuitive because we are telling the model that we don't care what you're going to do with the high wave numbers because we don't think that they are predictable. But we do demand what we do have an estimate what we think is predictable. Now you can ask, okay, so what happens with the high wave numbers? You don't punish it for being wrong. So it's true, we don't punish it for being wrong with their phase, but we do want to get the right spectrum. So we put a loss on the basically in spectral space, demanding the model to get the correct spectrum. And we do a few other tricks. And then we start training models, essentially. And we have trained them through the talk. I'll probably forget to mention when I show results, but we have trained models at different resolution. This is native era on the right here. And we have mostly with three different resolutions from like lower to higher. The higher resolution we train is 0.7 degrees. So let's say like a climate model, I would say. And this is kind of like a bit more complicated details on how things are really going. I should say that we're training our models for 3 to 5 day weather forecasts, trying to optimize over era 5. And what's the takeaway from here is the following. So basically, we have a dynamical core, like I said, and we have a physics-based parameterization. It's a single column. It's kind of the structure of all traditional models in the atmosphere. And the one thing we do that is a bit tricky, we have a set of inputs. So we initialize our state from era 5, but since our model runs with sigma coordinates, which is kind of like pressure divided by pressure surface, and era 5 gives you like its output in pressure levels, we needed basically to interpolate between them. But these are details. But essentially, we run our model, we run it, eventually we get an output and we try to optimize it. Basically, optimize it, getting the targets from era 5. So let's talk about what the results of this model. So neural GCM, if you put it against all these pure machine learning models, neural GCM is currently leading the like weather bench 2. So this model, in terms of weather forecasting, at least in some metric, this is 3 days of 500 hectopascal geopotential. Neural GCM is competitive with all previous models and the models that came after it. But I think the more interesting question, does it give you realistic like simulations? In what sense? And this is again 10-day prediction. On the left, you can see era 5 reanalysis. On the right is GraphCast. Both of them has a quarter degree. Neural GCM is at a lower resolution. But you can see that although neural GCM is at a lower resolution, it still keeps the structure much better than GraphCast. So it keeps the spectrum, does not blur more and more with time. So the atmosphere looks much more realistic. Clearly, it's not perfect. Also, it has a lower resolution compared to era 5. But so in that point, we were happy. And what we weren't happy about is that we now wanted to create basically stochastic model. And why we wanted to create a stochastic model? Because for weather forecasting, the real question is, can you produce like ensemble of weather forecasts when you see what's the probability of rain? It means that people just ran like basically multiple initial conditions, they perturb them, and they told you 30% you're going to have rain, or where a tropical cyclone will land. Basically, EC and WF runs like 50 ensemble members, and each one lands somewhere else. And this is kind of where like this kind of manifold that you see tropical cyclone where they will land. And to do that, we needed to do something different because we needed to like bring stochasticity to our model. And let's talk about it. So the idea we had was, let's plug in a perturbation to our model. So what kind of a perturbation? We will plug in some kind of a random field to our network. Now, this already raises an issue because when you plug in a random field to your network, probably it will try to ignore it if it doesn't help it to optimize something that it tries to optimize. So we needed to think of a different loss function. So the idea is, I'll repeat it because it was quite fast. We have the same setup as before, but now one of the inputs of our network is just some kind of a random field that develops with time and space. It has some kind of a spatial correlation and temporal correlation. If you are familiar with SPPT, this kind of stochastic parameterizations, it's broadly speaking, it's a similar idea to how physics-based models are doing that. Okay, so now we have a stochastic model, but we need to find a new function, new loss function to optimize, because mean square error would just learn to ignore this stochastic component. And what we have used is called CRPS, or continuous ranked probability score, and it has two terms. One term is just to minimize basically the error, kind of what you expect. You want to get more accurate prediction. So X is like our prediction, Y is era 5. But the second term is that basically every time we optimize the model, we launch two forecasts with two different random fields. And we want to demand that they will have larger and larger spread. So the idea here is that you have two terms. One is encouraging spread in terms of your prediction. So a blurry model would do very bad because you won't have a big spread. And the second is that we want to encourage the accuracy of our prediction. So we train our models, and this is kind of the score we get. So this is 500, like 500 millibar hectopascal of the geopotential versus lead time. And you can see that, let's say, this is the best deterministic physics-based model in orange. This is GraphCast in green. ECMWF ensemble is in gray, and neural GCM is in blue. So already outperforming ECMWF. On the right, it's CRPS. This is kind of the more correct metric to evaluate stochastic models. And so neural GCM was the first kind of machine learning model to outperform ECMWF ensemble weather forecast on almost all metrics. Okay, so again, I think that beyond looking on these scores, I think more importantly is to kind of trying to understand if your forecasts are realistic. Do they resemble something that you would recognize from the atmosphere? And I want to do here some kind of a Turing test. These are three predictions from three simulations. One of them is ERA 5. Two of them are two members of neural GCM ensemble. And you can take a minute to look at it. It's 15 days prediction, and try to guess which one is ERA 5 and which are the two from neural GCM. Someone wants to guess, feel free. And maybe tell me why you think. So maybe some of, yeah, go ahead.
It's oh, two. I was going to say option C was neural GCM. But
two options are neural GCM.
yeah, I see that now.
What?
I see that now. I was thinking there was one, but okay, never mind.
But which one? Okay.
I thought C was definitely a neural GCM. Maybe not.
Why?
I see like wave, like little. I noticed earlier videos or loops. There was like a waviness to the field, and I see that in the southern oceans.
Okay. So actually, what you guessed was ERA 5. It's the only one that was ERA 5. The point is, maybe you can find, I mean, I think that if I will tell you to focus on the right things, you would know which one is ERA 5. But the point is that we are very close to this Turing test. You would not be able to distinguish between ERA 5 and our predictions. So this is pretty different compared to, let's say, the blurriness you've seen in the previous ML models.
What are the right things to focus on? Curious now.
I focus on the ITCZ, and you'll notice that ERA 5 has slightly higher values there. I should say that this is probably, we are fixing it with the, I'll talk in the end, but like in this version of the model, we basically, ERA 5 had higher values, slightly, the extreme values of like total precipitable water is slightly higher in ERA 5 than in our model. So what we can do with that, we can start like talking about what people do with ensemble forecasting. So let's say here we're talking about 5-day forecasts of Hurricane Laura in 2020. Of course, we didn't train on that. You can see on the left the ensemble of ECMWF. On black is the right track. On the right is our forecast. And the big difference, I mean, you can argue which one is more accurate. The big difference is the cost. That basically we are like 5 to 6 orders of magnitude cheaper than ECMWF. So that is a big win, I think. And so this is kind of where we end the story about weather forecasting and what we have done. And our group is mostly nowadays is focused on like applications of longer simulations. And let's talk a bit about what we can do with this model for simulations of climate. So we just we trained it for 3 to 5 days weather forecast, and we tried to run it over longer and longer period. And we have noticed that we have models that are stable. So here I'm showing the global mean temperature versus time for a specific realization of neural GCM. And we can run many different initial conditions, and we can look at their mean. And then we can ask, do they do a good job compared to ERA 5? And the question is that yes. That like ERA 5 is the orange one. And you can see that broadly speaking, ERA 5 looks like a realization, one of the realizations of neural GCM. And we prescribe, I should say that we prescribe boundary conditions here. We are an atmospheric only model at the moment. And then we decided to start comparing against the best available physics-based models. So for 1 year timescales, we have nowadays a global cloud resolving models that ran for 1 year. They are very expensive. They are high resolution models. They like running 1 year in one of these in X-Shields, a model that ran for 1 year is $80,000. It runs on 13,000 CPUs. It's very slow. Our model costs 8 cents to run, and it runs on a single TPU machine. And then you can ask, okay, so which one of them are better? And what we've looked at many metrics, we just saw that we have over 1 year, when you average our climatology, we just do better. So in this case, we are showing total precipitable water. So you can see this is the bias from X shields, this is the bias from neural GCM. And it's not that only in the average we get things correct. Even if you looked on some kind of emerging phenomena, here I'm focusing on tropical cyclone, it's a 1 year. Like orange shows trajectories from Euro 5, blue trajectories from neural GCM. And you can see that basically when you run this free run of neural GCM with prescribed boundary conditions, it produces kind of the right tracks at the right time. It shouldn't match exactly. We're talking about, it's not like weather prediction scenario. We are running it over 1 year. It's not predictable, but it predicts then roughly the right number of a tropical cyclone in the right place in the right time. So after doing that, we have asked the question, can we run even longer simulations? Okay, so we've done 1 year now. Can we run it for longer simulations? And what we found that sometimes we get instabilities in many of our models. So here I'm showing the global mean temperature versus time. And orange, you can see Euro 5, in blue is our model, and you can see that it ran maybe for, I don't know, 20 years here and then had instability. Sometimes we get models that has climate drift. So you can see basically that neural GCM becomes warmer and warmer with time compared to Euro 5 that also becomes warmer, but at a different rate. But sometimes we don't know why. We don't know how to control it. We don't get these things. We got models that are much more stable, that don't have a drift. So here I'm showing just like simulations of 40 years. I'm showing the global mean temperature in these simulations per year. And you can see this is like average over like 22 AMIP models, so traditional atmospheric models, versus ground truth, which is Euro 5, and neural GCM in blue. You can say, broadly speaking, neural GCM gets the trend correctly, gets how the effect of El Nino, let's say the 1998 El Nino, gets things correct. And it's not only that it gets correct in the trend. If you look now on the climatology of our model, so on the left, we have 22 ensemble members of neural GCM, all ran for 40 years. On the right, AMIP simulations, so traditional based models, 22 of them. And I'm asking, how well are they reproducing the temperature on Earth along these 40 years? So neural GCM, the root mean square bias, or mean square error, is much, much lower compared to AMIP models. So basically, even our worst run is better than the best AMIP existing model currently, or the 22 at least we compared against. Okay. So I want to go to the last section, which is new results. It's the first time I talk about it, about learning from observations. So this, all what I talked so far, it's in this Nature paper that was published like half a year ago. And now it's kind of the next version of our models and what we have done. And let's talk about why we need to learn from observations. First of all, let's look at Euro 5. And here I'm showing precipitation. And below, I'm looking at observation from GPCP. And I'm zooming into a section. And you can see that although Euro 5 is trying to reproduce like basically the state of the atmosphere, it just has the wrong precipitation pattern. Not only in terms of where it is exactly located, you can see the amplitudes are very different. So basically learning from Euro 5 precipitation is not ideal because Euro 5 is not a great model for precipitation. Also, people try to learn from global cloud resolving models. And even then, although they have certain aspects they present much better, they have certain aspects they don't do much better. Here I'm showing kind of the percentile versus precipitation rates. In blue is iMerge observations. In red, dotted red, is our CMIP6 models. In black is X-Shields. And you can, X-Shields is this global cloud resolving model. People have used it to learn, used hybrid models to try to learn from X-Shields. And you can see that X-Shields have roughly the same bias, at least at this resolution, the same bias as kind of CMIP6 models. So it's even if you really reproduce this global cloud resolving model, you'll still have issues. And this is why we wanted to start learning from observations. And generally, it's why it has been difficult. If you remember when I started the talk, I said this kind of so far, this single time step of learning, you needed to somehow diagnose what are the tendencies or fluxes of your model, and this is what the neural network has learned. And this is very difficult to do when you have a set of observations. Nobody gives you this quantity to learn. You need to somehow come up with it. But when you have an end-to-end training or online training, what people call, you just need to have something in your model that corresponds to the observation. And then you can optimize over it. You don't need to diagnose anything. So kind of the pure ML approach would be to say, okay, we just will have another output. We'll add somewhere along the neural network a new output of precipitation and optimize over it. This is, I would say, the pure ML approach, and you will see them already. There are a few attempts like that, and you'll see it more and more. They're just people using new output heads to predict new targets from observations. We have done it slightly different to keep physical consistency. Due to the lack of time, I don't want to get into that. But basically, we are conserving water. We are doing it in a more physically consistent way. I will be happy to talk later about it, what it means in that aspect. But I want to show a few results because I think they are pretty exciting. So here, I'll do another kind of like, I won't tell you yet the answer. Here I'm showing a Hofmüller diagram. So it's like tropical precipitation. The y-axis is the day of year. The longitude, the x-axis is longitude, and these are observations. And now we have here 4 different models. One of them is a global cloud resolving model, 2 are AMIPRANs, and 1 is neural GCM. You can try to think with yourself which one is the most similar to the observations before I kind of poison your mind and tell you that. Okay. So the second one, and I'm not objective. I totally agree. The second one is neural GCM. And you can see that even global cloud resolving model has, in many of the patterns and amplitude, you can see the differences compared to observations. At least they are very apparent and clearly like the AMIP-like style models, which are at lower resolution, they have even bigger differences typically. And it's not only visually compelling, I would argue. We have compared along, like this is 13-year runs. We have compared 37 neural GCM ensemble members to 37 AMIP models. And what we find is basically they are, and we are talking about precipitation bias, it's just more accurate, neural GCM. Not only more accurate than AMIP models, surprisingly, it's even more accurate than ERA5, at least when we compare it against iMerge that we have trained on. So, or at least comparable to ERA5. And this is surprising because ERA5 is initialized every 12 hours to match current state of the atmosphere. We are a free running, like just prescribing boundary conditions running for these 13 years, and we have lower biases, or at least comparable biases, let's say. And GPCP is a different set of observations I should mention. It's just kind of the differences between observation sets of precipitation. There is no like complete agreement between different observation sets of precipitation. Okay, and I started with extremes and I want to finish with extremes. And what we find that neural GCM can also simulate better extremes in many senses. So here is a map, and we are looking at on the 99.9th percentile of precipitation for these 13 years at every location. And you can see the arrow. This is neural GCM simulation above land, above ocean. This is ERA5. And I can add more and more models. Oops. This is GPCP, these observations. This is kind of the uncertainty from observations that we have. But you can see that these are like 5 different CMIP6 class models. They all have much larger like biases compared to neural GCM. And yeah, I have 5 more minutes. Okay. So I can keep on going, but basically I think you got the message. I'll just mention one more thing that is a big problem in simulating precipitation. So it's known that traditional models are don't simulate correctly the diurnal cycle of precipitation above land. So land typically has a maximum hour when it precipitates on average. And this is what the colors are indicating. These are observations. You can see brown is the time basically that like the diurnal cycle peaks in precipitation. On the right bottom, it's a physics-based model. Very typically, it shows an earlier peak. This is what happens in physics-based models. ERA5 even, although it's initialized every 12 hours, still have this problem. And neural GCM, I would argue, is much more similar in terms. What you need to compare is the colors above land. Is the kind of something you want to focus on. Okay, so I'll take a summary and I want to make a few remarks. So what I try to argue that differentiable atmospheric models are really useful. We have used them in one particular way. We have trained a hybrid model to create like a model that is has a good skill in weather forecasting, has a realistic atmospheric state, all accurate decadal simulation, and so on. But you can think of using it in a completely different manner. You might say, I don't like at all neural networks. I think that it's a bad idea. We don't understand them. But you can still use our differentiable atmospheric model to optimize whatever parameterization you want to optimize over. If you don't like neural networks, that's fine. I agree on certain aspects for sure. So I think that it has a lot of potential for many different use cases. I'm happy to talk offline about that. And I should also acknowledge that this was a huge team effort. Like I would have never been able to do it alone. Like all of us contributed, basically worked full time on it for a long duration. This is a huge project, and it's really, really a team effort. It's not something that I think one person can do. And like Dima, Ian, Stefan, and Peter were like basically, yeah, it's just I want to highlight that it's a really team effort and not a single person. The last thing, and no, one before the last, we have a GitHub page where you can run our model, you can play with it. Please visit, think about ideas. There is an active questions. We try to answer the stuff that people ask, how to use, how to do stuff. I really recommend you, if you're interested in it, to have a look and see what you think. We have examples there, and I think it's going to improve. We hope it's going to improve more and more with time. We still have, okay, so far I kind of talked about a lot of success and how we outperform in certain aspects traditional models. We are very far away from being a full climate model, really, really far away. We don't have many of the components that the climate model has. We don't have a land model. We don't have chemistry. We don't have sea ice. We don't have a coupled ocean model. So all of these things are really difficult things to do. We are an atmospheric only models, and we want to experiment with coupling to other models, which we are trying. There are different ways to do that. We still have, I would say, maybe if you are thinking of climate projections, I think that we are all in our team currently a bit skeptical about the possibility of extrapolating. So to, let's say, operate very well in completely out of sample, although we have tested our model in +1 degree SST, +2 degrees, and +4 degrees, I can tell you that +2, it still behaves fine. +4, it behaves it just spits out garbage. And there are multiple challenges. It's not the end of the work here. This is kind of, I would argue, it just opens a lot of doors to do atmospheric modeling or climate modeling in a new way. And this is kind of what I want to end with.
The other mic, I don't know where it is. So if someone sees it, let me know. Anyone in the room have any questions?
Thanks a lot for the talk. When you mentioned you add stochasticity with the Gaussian noise, are those correlation time and time scale learnable parameters in your model?
Yeah, they're just learnable parameters. We have 10 correlation times and 10 correlation lengths that we just learned.
Oh, for each wave number?
Yeah, it's basically a Gaussian random field. It's not for each wave number. We just learned it's basically 10 Gaussian fields that each one of them has a correlation in time and in length. And it's 10 learnable parameters, 10 learnable time correlations, and 10 learnable special correlation.
Okay.
It's 20 parameters.
Can I ask a second one?
Yeah.
So when you say sometimes by serendipity you have a model that's stable, is it stable for all stochastic realization?
Yeah, okay. So I should highlight that we don't know how to create stable models except by luck, I would say, that we train several models, and we have no clue. Currently, we have changed stuff, we have learned many stuff, but the bottom line is that we are still in the point that we can nowadays create much more stable model than what we created in the paper that we wrote, but it's still based on luck. Some of the problems, but the stochasticity, if they are stable for all stochastic perturbations, I mean, the Gaussian, I'm not sure, like if you would enter something crazy to the network, I'm sure it won't work, but the Gaussian random fields are bounded on like their amplitude. I mean, they have trained with it. So this is not the source of, I mean, this is not the source of instability. I mean, we had also instabilities in the deterministic models. It's not, was not nothing to do with the noise.
We do have a question online. Would you like to unmute yourself and ask the question?
Sure, thank you. Great talk. Really learn a lot. Excellent. One quick question that in your paper and also in your presentation, you
Nachikita, you have a question?
can you hear me?
Oh, we can't hear. Okay, we can't hear you in the room. Do you mind putting your question in the chat? Both. Sorry, I think something's going on with the sound from Zoom. So feel free to put your question in the chat. In the meantime, Jatan, do you have your?
Yeah, thanks for a great talk. I have a question as to like your future directions. Even when I first read your paper, I was like, you're like the 4 Kelvin, like, warming, maybe that's end of the century situation. It just feels like you're setting like that benchmark is rather rigorous. I mean, it would be very interesting to even do like decadal predictions.
Yeah.
Because those.
This is what we are doing. Our direction is that we are coupling an ocean model, and we are trying to have like, again, all in the, I don't know when it will come out. We have like, but in the previous model, we didn't have a realistic stratosphere. I mean, realistic in the sense that we had enough even levels in the stratosphere. You need a lot of levels in the stratosphere. And we are trying, this is like, broadly speaking, our aim is to do that. Like, I don't know, we call it climate nowcasting or whatever you want to call it. But basically to understand current weather, like what does it mean a 1 in 100-year storm? What does it mean a 1 in 1,000-year precipitation event? And B, what is the possibilities of the next 10 years to look like? I should say we are lacking many of the components that someone would argue are really important. We don't have aerosols, we don't have CO2 in our model. I mean, we don't have chemistry at all. So again, I just want to like surface the caveats that, but we do think that we are able to simulate current climate in a with very high skill compared to at least baselines that we have compared against. And I think it would be very, very beneficial to have a baseline for all models that come. I mean, we try to make tons of evaluations. Our supplementary is something like, I think it's like 80 pages or something, but like someone else will come with his own evaluation. And I'm like, one thing that I really think would be super helpful, that it would be standardized evaluation for climate models. And I think there are certain, in the non-ML things, there are certain things, but I think that there are emerging groups who try to kind of build a much more coherent that will apply both to ML and non-ML. ML can cheat in many senses, and yeah.
Yeah, I only sort of, thank you, this is very clarifying. I only brought this up because I'm sure you've come across this, but there's this like series of papers now that calling even editorials in New York Times saying like, oh, we need to operationalize climate modeling, right? And I feel, like, okay, fine, if a government center says that, maybe there's money for that, maybe there's not. But I think if for instance, if Neural GCM can maybe even lay a preliminary benchmark, because you beat AMIP, and at 10 years maybe prescribed SSTs will be fine, modulo whatever. But I think that could be like already like a good place for like even agencies to like start being like, hey, now we have like a differentiable model. Maybe it doesn't have the full chemistry, but already we can set like decadal, maybe 5-year benchmarks that we can maybe target. So I mean that's what I was coming from. Like, yeah, who knows what will happen by the end of the century, but maybe we can do something.
Yeah, I mean, I broadly speaking, I agree that it's a realistic target. Unlike like, I think we are. Who knows? Someone will develop something different. I don't think we are equipped now to do projections to 2100, but I think that we could simulate. Once we have a realistic, I don't know, variability of the ocean and many other components, and maybe we will not have all the aspects, because I don't know, like we won't have certain tipping points in our model. I don't know, and their effects. So you could criticize also like the limitations of this approach compared to a more comprehensive approach. But broadly speaking, I agree. This is one of the kind of, we have many like things in the middle. Let's say training from observations was that we want to have a model that really has a really good precipitation, because this is one of the things that we're going to ask and people are interested in. But also it has limitations. I didn't say it's a low resolution model. We want a much higher resolution. I mean, there are many kind of directions you can work on that still.
Thank you.
Now, Chiquita, could you try unmuting yourself one more time?
Can you hear me now?
Or Pierre, if someone online could try.
Can you hear?
Okay. Okay, it doesn't seem like it's working right now. So I'm just going to read it out loud. In your talk, you showed the comparison of neural GCM and AMIP for climate change. One quick question: do you plan to run neural GCM for S2S and seasonal forecast? Is it okay to run neural GCM for 45 days? So parentheses, S2S and seasonal scale.
Yeah, so definitely the answer is yes. We've run some, I know even someone, we have run it. The limitation is that we don't have an ocean model. So I ran it just for fun with prescribed sea surface temperature, gives you an unfair advantage compared to, let's say, ECMWF product or constant sea surface temperature. And we are better when we are prescribing sea surface temperature. We are worse when we don't change sea surface temperature. So the next step, you need an ocean model. But the answer is yes. Like it's one of the, we have kind of this kind of roadmap that this is one of the things we want to verify, that we are doing a reasonable job in S2S. And like, again, S2S has limitations generally, but like, yeah, the answer, yes, we do plan to.
Thank you.
Yeah.
We have 2 more questions online from Pierre Gentine. Thank you a lot for the great talk. I'm very personally interested in differentiability, and we are working actively in that space. We'll send a paper we just did on the topic. I really enjoyed your paper and seeing that you built the first full end-to-end hybrid model. I have a question, though, regarding comparison to pure ML-based models. One could argue that the DICOR is quite learnable. One advantage of pure ML is that it is computationally cheaper. Have you tried the exercise of learning the DICOR within the same nice metric framework that you have?
Yeah, so what we have done is run a pure ML with a single column, like remove the dynamics, which is like not really exactly a comparison, but like when you run a single column pure ML model, it doesn't do great. We have it included in our supplementary. We haven't done it like the exact same configuration with a pure ML. For the weather forecasting, I agree that likely pure ML would be enough. For the climate question, I think it's less clear. Currently, we don't have this kind of pure ML for climate doing very well, although there are certain attempts that did run for decadal stuff, but like the baseline was like mimicking an existing model. I don't think it's impossible that pure ML, I mean, we don't have like the evidence that we must have the DICOR. There is no like, we didn't find the evidence, and it's not was lack of trying, but we just don't have the evidence. Personally, I like the idea. It gives you a lot of interpretability in many cases. For example, the case, maybe I'll show just one thing, like which is kind of related. Let me check that. I have it here. So what we have done is trying to ask what advantage gives this kind of physical like the DICOR. Okay, I don't have this plot here. I think it's a great question. We don't have the proof. We think plausible that pure ML approach would eventually do many of the same things. I think some of the things there can't. I just give an example because, for example, precipitation. We take a completely different data set and we learn how things should, like how precipitation should look like. But because we have a physically consistent model, precipitation in our framework is coming from integrating the water budget. So in order to change precipitation, the model needs to change how specific humidity and cloud fields look like. So we don't anymore only want to optimize over era 5 because we know era 5 is wrong. And by predicting, I don't have the figure here, but I'm happy to send it. We show that when we are trying to optimize over precipitation, it leads to other changes, which you can, it's still, I wouldn't say we have a proof, but there are a lot, they shifting to a bit more similar and being consistent with, let's say, specific humidity observations. So it's not exactly a proof. I think that many of the things we've done eventually, maybe a pure ML approach could do. We don't, yeah. So I don't, it's a.
Thank you. We do have one more question online. Very instigating talk. I wonder what are the challenges you envision on integrating other ES components, for example, land, in a certain way it could be in a set of multiple modalities. How do you see this task? As once you start integrating, feedbacks then will need to be passed and reflected across these components during training time.
Yeah, I mean, like, let's talk about the ocean. You want to build a differentiable ocean model. This is kind of what we do. But first of all, if you really want it to be based on physics, you don't have data to optimize over, at least in the depth. Maybe you have SST. So there are data issues many times. You could complement our approach with physics-based models. Like, just say, I just want a differentiable ocean model. And I think one of these exists. I can't remember the name of it, but some group that I've talked to.
Veros.
Yeah, Veros. And so you can imagine start coupling these kind of differentiable things. You might go to the approach that, like current models, kind of optimize each model separately and start fusing them together. But the problem is we don't have the same concepts always. Let's say we don't have the concept of, I don't know, surface evaporation. So we would need to add it to our atmospheric model, and it's not very easy. Or you could do that in all sorts of ways, but it's not very clear always how to do that. So it would be self-consistent. So the amount of water that evaporated to the atmosphere are inserted into the land. I mean, there are so many challenges there, I think. But like, so we have data challenges. We have how to make it physically consistent. I think it's really, really challenging. We really want to say that we are 4 people currently working on it. We really, really encourage everyone to do stuff with that. We know that there is a group, I think, that is trying to insert traditional-based parameterization and optimize over those. I think that would be super interesting. Maybe you can accompany what we've done with radiation code that is physics-based code that is written in a differentiable way. I mean, there are tons of things I think you could do with that. We definitely are not capable of doing many of those, but yeah, it's not easy, the question of coupling and how, and definitely not in the sense that it will be physically consistent. I think it would be challenging to have pure ML models coupled. I think it would be easier.
Thank you. We'll take one last question in the room, and then we're almost at time.
Thank you for the very great talk. I just have a little question. It might be a detail, but I was very interested in the filtered mean square error. And I was wondering if you end up finding kind of a cutoff frequency for the space, meaning that, for instance, if you get a low mean square error at 100 kilometers, so you capture convective organization, it's sufficient to then improve your predicting score. So yeah, I was just wondering if like you can map also the filtered mean square error with the uncertainty at each scales you're.
So okay, I'm not sure I'm going to answer exactly what you asked, so correct me. So how we decided how to filter things was to look at physics-based model and say, okay, this is how physics-based models kind of like the error growth happens. And then we filter it gradually. For every field, we do it differently. So temperature and moisture and clouds are not on the same thing. And we demand our model to be a bit better than the physics-based models because we hope that we could capture more. So if we kind of truncate it and say this is what physics-based models are doing, maybe we won't be able to surpass them. I should also add, not sure if this is what you asked, that we have tested our model with a mean square error, like just running it with a mean square error. Like I honestly thought that having a single column structure would be enough to keep the coherence of the atmosphere, that it won't blur. But it was smart enough to fool us. Although it's a single column parameterization applied everywhere, to still blur. Like our initial expectation was that enough that we have this single column parameterization. And then another thing, not sure that you asked it, because that when we train only with a mean square error, we get a better mean square error, clearly. So doing that didn't help the mean square error. Like it harmed our performance in a sense. We could get better performance if what you're interested is a mean square error. So not sure I completely ask. I don't think that we have, I think that the kind of eureka moment that we had was that we need to, like, for me, is not the one who thought about this idea, it was Dima. When he told me this idea, I told him, this doesn't make any sense. You are blurring your targets, and you expect that blurring your targets will sharpen your model. To me, it took a while to understand why it would be like that. Like I needed a lot of plots to think why it would happen. So I don't think, I mean, we didn't use like it was kind of hand waving how to cut off. I mean, looking at physics-based models, there is nothing like instrumental in what we've done except looking on what, like how physics-based models behave in terms of like their predictability, like how far they can predict into the future different variables. But I say that this whole deterministic thing, eventually we think that this is not the way to go forward, because this was like, if you read the paper, you'll see we've needed to add, every time we got a new issue with the model, and we needed to add a new loss. And eventually we've solved these issues by adding like 4 or 5 or 6 loss terms. But it's really, really not elegant compared to this kind of single loss that you can use the CRPS that kind of automatically basically aims at getting the right distribution. And this is what we were really aiming for. You want to get the right distribution. You don't want to add like 6 loss terms. We added some terms, and then we saw we have a bias on the high frequencies. We had the loss on the high frequency. I mean, it was kind of a very painful and not intelligent process, honestly. Like, I mean, this is how you do research, right? You do silly stuff. It roughly worked, but we are all like, when we are continuing, I can guarantee you we are continuing only with our stochastic model. We think it's a much more elegant and useful like way to do stuff.
Thank you again for your great talk today.